Hello, welcome to uh, video for methodology 7.1, sort of a basic form of undetermined coefficients. I've done a video of undetermined coefficients method before, and I kind of approached the more advanced version of it. And so I've now kind of broken that into two separate methodologies, and that other one is methodology 7.2. Um, and I think you do want to see this one first, and then sometimes just use this basic form, and then kind of decide when you would use which version. So the instructor model example we're going to look at is y double prime minus 4y prime plus 4y equals e to the 3x, with initial conditions y of 0 equals 2, y prime of 0 equals 0. And step one is essentially methodology 6.2, solving the second order linear constant coefficients homogeneous case. Um, but we will go through that to start off. So to get the homogeneous form, we just replace the forcing function with 0. Remember there we go to the characteristic equation. And then we solve that. In this case, it is factorable. And we get the repeated root r equals 2. So for the fundamental set of solutions, y1 is e to the 2x, and then to get a linearly independent solution, y2, we multiply by x. And we kind of set those aside, though when we're choosing the particular solution, we do ensure linear independence with y1 and y2. Now, in the choice of the particular solution, we look at the form or type of forcing function we have. And since we have e to the 3x, we know we're going to want to choose yp to be a constant times e to the 3x, because that 3 won't change when we take derivatives, but we don't know what needs to be out front to give us e to the 3x on the right. And again, we've been kind of referring to this table here. And so we're kind of looking at this row of the table where the forcing function is a constant times e to a constant times x. So a is 1 and b is 3. And then our particular solution is capital A, which is undetermined, times e to the 3x. All right, now that we have the particular solution, we're ready for step 3, which is to take the first and second derivatives. And so these are pretty easy derivatives. We get the same exponential back, but the chain rule gives us extra 3. That's why p prime. And another 3 for the second derivative, 9 times a e to the 3x. Once you have those, you're ready to substitute the results from steps 2 and 3 into the non-homogeneous differential equation that was given at the very beginning. Right. So for that second derivative, we'll use the 9a e to the 3x, and then minus 4 times the first derivative, 3a e to the 3x, and then plus 4 times the particular solution itself, a e to the 3x. And then on the right side, we just have an e to the 3x. All right. And we should be able to solve that and figure out what a is. So that capital A is our undetermined coefficient. So for simplifying this, we don't have a whole lot to do, but um, we can divide everything by e to the 3x. Remember, e to the 3x is non-zero, so it's okay to do this. And then we get the simplified version, 9a minus 12a plus 4a equals 1. And so this equation, once the exponential is gone, may have constant terms, linear terms, quadratic terms, etc. And so the number of different types of terms will match the number of different undetermined coefficients. So if you only have one undetermined coefficient, then you probably just have uh, an equation for your constants, like we do. And in that case, it is just this equation, 9a minus 12a plus 4a. And so that ends up just telling you that uh, a equals 1. But in general, we may have another undetermined coefficient. And then in that case, we would have um, linear terms. And you notice there's no linear term on the right, but we could think of there being, a 0x. So we would get a separate equation for the linear terms that have x. In this case, b equals 0. And if you have a c, then there should be x squared, and you'll get an equation for x squared. So in general, this can be a system of equations for the undetermined coefficients. Um, and the dimensions of that really is equal to the number of different undetermined coefficients you have. So solve that system of equations, using the like terms to identify which goes in which equation, right? You could also have cx squared plus, or let's say we did have an x squared over there, right? If it was a minus x squared, then I'd have an equation for x squared, and it would be c equals -1, right? So if there's no term on the one side of that type, then just put a 0 in. But in general, you'll kind of get these, and you could solve those using any techniques for solving systems of linear equations. So that's just showing you how step 5 can be a little more involved than it is here. All right, so going to step 6, state and validate the particular solution. Remember, A isn't the particular solution, right? The particular solution was that y p equals a e to the 3x. So we're now able to get this as a is 1, it's actually just e to the 3x. So this is kind of a special case where the particular solution matches up exactly with the forcing function. In general, that doesn't happen. So for validating that, we would take derivatives. And then those get substituted into the original differential equation. And then you could see that this does work, right? We have 9 minus 12 plus 4, which equals e to the 3x. Now, remember that particular solution is a term that's added on to c1y1 plus c2y2 to get us our general solution. And we found y1 was e to the 2x, and y2 was x e to the 2x. And then particular solution being added on is e to the 3x. So there's our general solution. Now we had initial conditions here, so we can find a specific solution. Our initial conditions, y of 0 equals 2, and y prime of 0 equals 0. So if we put in y of 0 equals 2, we replace all the x's with 0, and then 2 on the left. And then that's actually 0 there. So you guys should get c1 equal to 1 here. Now you don't always get that lucky. Sometimes you get a system of equations here as well. So now we know C1 equals 1. We can replace it with 1, which just makes it go away, right? And then we need to take the derivative to apply the other initial condition. So the derivative, we get 2e to the 2x, and then using the product rule there, e to the 2x plus 2x e to the 2x, and then 3e to the 3x. And then if we put in the initial condition y of 0 equals 0, we get 2 plus c2 plus 3. So that tells us that c2 equals -5. All right, now that's actually not the end here. We now need to write out that specific solution. So, I guess I could do that. Well, I'm going to do it on a separate line. There's a common issue of students just kind of stopping right here and leaving that specific solution to be implied. Even though all the information's there, we do want to rewrite it, putting in C1 and C2. So we can put C1 back there. All right, and that is our specific solution. So I don't have us validating that final specific solution, though you could. I figure at this point, the focus on validation is on the particular solution. So I had us validate right there. But you can validate at the very end as well. Never hurts to do some extra validation. So ready to go on to the fill in the blanks and your turn examples. And I use the same homogeneous form for example 2, so you can focus more on finding the particular solution. But you notice that here we do have 2 undetermined coefficients, A and B. And so when we get to step 5, we do have 2 equations. So there'll be the constant terms get all set up equal to each other, and then the x or linear terms get set equal to each other. So we have 2 equations, 2 unknowns. We can find A and B that way. Right. And then with your turn, we got a sine function for forcing function. And so remember how we set up the particular solution there. We talked about that in the overview video. All right, that's going to do it for this methodology. Again, there's a methodology 7.2 that does more of the advanced version of undetermined coefficients. And that's really for kind of the lower half of this table when you have an exponential times something more complicated. The technique I just showed is good for kind of the top half, where you can just take derivatives and substitute it in. But if you think about taking 2 derivatives and substituting with some of these more complicated ones, it really becomes unmanageable to do that without making some mistakes. So I give you a different approach. All right, thank you. See you in the next video.